Let's talk about chapter 6.8. Before we get into the calculus of it, let's talk about a situation where the calculus of chapter 6.8 can come up. I found online a data set of calls to the Toronto Fire Department, and it had, tens of thousands of rows, and it had something like where the call for service came from, or where the fire department was needed, what type it was, and the day and time it came in. It was about 2 months of data. And I've took the difference between this call and this call, so that would be what, an 8-minute difference? And the difference between this call and this call would be 1 minute. The difference between this call and this call would be 2 minutes. So just the time from one call coming into the next, and that the average of all those numbers was just above 4. So what do you think if I made a histogram of all these numbers, the 8, the 1, and the 2, thousands and thousands of these, with an average of 4.1-ish, what do you think that histogram might look like? Now, the shape of this histogram will influence how many dispatchers you need to handle the load without getting busy during surges and stuff. So it's a pretty important thing to think about. So anytime you think of a histogram with an average of some particular number, you might expect to say, well, there's the mean, and maybe it's kind of a bell curve around the mean. We're talking histogram, so there would actually be kind of bars here, right? So let's go see the data and see what we find. So here's the data set. You can see it has a little more detail than I mentioned. It has prime street, cross street, the latitude, longitude, what type of call it was, and here's the dispatch time. Alarm level, all kinds of stuff. So here I'm taking differences. Apparently the original data set wasn't sorted exactly earliest to latest, so that's okay. We can resort it, and here's how many minutes were between this call and this call, and I've rounded them, so if it was a fractional number of minutes, like 0.7 became 1 minute. And then I made a histogram here. How many of these time from call to call was 1 minute, how many were 2 minutes, how many were 3 minutes. So there's a fun count if going on there. And then just dividing each number by the total number of calls to get percentages. And here I'm taking the mean of all those. And then here's what the histogram looks like. Is this what you thought it would look like? Well, it doesn't look like what I drew on the paper, right? I drew something that was kind of like a bell curve, but apparently this has a really strong right skewness to it. So even though the mean is here about 4, it's not like it kind of concentrates around 4. So we need to be able to fit a curve to the height of these histogram bars. So what we can do, instead of plotting histogram bars, plot each one as a dot vertically, and then do a trend line. Now I think we would agree that this linear trend line is not doing a good job capturing what's going on with the data. So which of these other options do you think would do a good job? Some people might say, well, this looks like kind of 1 over x. So that would be a power model, x to the negative 1. So let's try that. And that seems to really not fit near the beginning here. What if we tried a polynomial, a quadratic? Well, that goes below 0 and then starts increasing again for really long times between calls. That doesn't seem like a good idea. Logarithmic, that goes below 0. We don't like that. We tried linear already. How about exponential? Does that look like kind of exponential fall off? That looks kind of reasonable. If you know what an r-squared value is, you know r-squared near 1 is usually the best, and this is pretty close to 1. If you don't know about r-squared, that's okay. You can ask me sometime or take my stats class. So this exponential model seems pretty good. Another thing we have to think about is when we were looking at the histogram bars thing, these histogram bars have to add up to 100%, right? That's just however many calls you have divided into all these different bins, still has to add up to 100%. But there's no guarantee that this exponential function kind of adds up to 100%. So that's what we're going to be talking about in chapter 6.8, the math of checking whether a model like this adds up to 100% or not. And where would we stop? I mean, here we're stopping at 23, but really you could have a time between calls of 24, 25, 26, 30 minutes, 45 minutes, 60 minutes, 120 minutes. it's hard to know where to stop. So we're actually going to say, let's not pick a place to stop. Let's integrate all the way to infinity. Let's come back and look at the paper and pencil thing. So our actual curve was more like this, and it was some number times e to the negative some other number times t, and we're saying we want the area under that to be 100%, just like the area under the bars, or the sum of all the bar heights was 100%. So the name for this kind of endeavor is Industrial Engineering and Operations Research, or also Management Science. And that's what I got my PhD in, so you can imagine why I would be interested in this kind of thing. So I think some people have some idea of what mechanical engineers do and electrical engineers and chemical engineers and stuff, but what do industrial engineers do? They organize systems in industry and business and government and nonprofit work. All right, next we'll do an overview of chapter 6.8 because it's a big chapter.